So what is a heat transfer? Now if we say heat transfer, that is the process of transmitting heat, from one place to the another, from one object to the another, or from one region to the another. That is what we call as the heat transfer. So there are three actually techniques associated with the heat transfer. So we have what we call as the conduction. We have what we call as the conduction. So what is the conduction as a technique of a heat transfer? This is the heat transfer that involves the heating, actually that involves the physical contact of the two objects or the two regions. So that is the conduction as the heat transfer. So the heat is transferred whenever there is a physical contact between the two objects or the two regions. Let's say we have this is the object A, and it is in contact with the object B. Now if object A has the more internal energy than object B, then the heat will be transferred to this object. That's what we call as the conduction. And let's say if we have the chain of the, let's say, the contact objects, so the heat will keep on actually transferred like that. So that's how the conduction works. And basically, if we consider, let's say, a metal bar. Let's say we have the metal bar. A metal bar is composed of the particles. So let's say these are the particles of the metal bar, and that should be that. And the particles are actually at the thermal contacts. Now if we apply the heat in this section, so this is actually this particle will have more internal energy than this, then the heat will keep on being transferred until the other end of the metal bar. That is the actually conduction. That is the principle being applied whenever there is a physical contact between the two objects or between the two actual particles. And we also have what we call as the convection. So convection. So what is a convection? A convection, this is the heat transfer through the movement of actually fluids, like let's say the liquid and also gas. So that's what we call it as a convection. So what happens during the convection? So the thing is that, let's say we have a system. Let's say we have a system of gases. Let's say we have the system of the gases in a container like this. We have the system of the gases in a container like this. Now let's say we apply heat on the bottom surface of the container. So now what happens is that the air particles down here will gain more kinetic energy, thereby they will become less denser. If that is the case, then the actually particles will tend to go up like that. And the air particles up here, they are more denser than the bottom particles, therefore they will sink down, and the process will keep on actually the process will be continuously occur. That is what we call it as the convection. That is what we call it as the convection. And also if we take it on the perspective of, let's say, if we have, this is a pot, let me have yeah, that should be given as a pot, and we have the water inside. Let's say this is the water inside the pot. Let's say this is the water. Now what happens if we happens to, what happens whenever the water get hot. Let's say this is the fire. This is the fire being applied down here. So what happens is that the bottom water will get hot first. So in this case, it will become less denser, thereby making to be going up, and the surface water will be more denser, thereby it will sink. So the process keeps on going, keeps on going, keeps on going. That's the principle behind the convection, as the mechanism of the heat actually transfer. Then finally we have what we call it as the radiation. So on the radiation, this is the transfer of heat through electromagnetic waves. It does not necessarily need a medium to travel, but this process occurs in what we call it as a vacuum. So by the way, on the radiation, let's say we have, this is the object. Let's say this is the object with high temperature. That should be with the high temperature. That is with more internal energy. And there is someone here. There is someone here. Like that. So what happens is that there's no physical contact between the object and the person. But what happens is that this person happens to feel the heat from the actual object. So how do you think that heat has been transferred from this to this person? So the heat has been transferred in form of electromagnetic waves. Those are the waves with two components. So electromagnetic waves contains what we call it as the electric waves, and contains electric component and also the magnetic component. We call them as the electromagnetic waves. So the heat is transferred in form of the waves. So keep that in mind. It does not need to have the physical contact, or there is no need of a media for the heat transfer. So what is that one? That's what we call it as the radiation. So the heat is just being radiated through the vacuum. So that is what we call it as the radiation. So now we would like to quantify the mechanisms of the heat transfers, basically conduction and also the radiation. Now, how should we quantify these actually two mechanisms? Let's start with the actual conduction. Let's say we have a metal bar like this. Let's say this is the metal bar with a cross-section area given as A, like that. And let's say the length of the metal bar is given as L, and that should be that. So now let's think of applying heat onto this section. Let's think of applying heat on this section. Let's say given as Q. If that is the case, then let's say the temperature in this end is given as T1, like that. And since this section is the section of high temperature, then the heat will be transferred from this end and to this end via conduction. And let's say the temperature in this end is given as T2, like that. And let's say the time takes for the heat to be transferred from this end to this end is given as some sort of T. So what is the heat being transferred? So the heat being transferred is given as, a K, which is a conductivity of a material, times the cross-section area times the change in temperature between the two ends. between the two ends, and divide by, let me have it here, times the change in temperature, divide by, and that should be the length of a conductor, and the times time. This is the formula that is being used to express the heat being transferred via conduction. But you should have to understand that the power is given as the heat, energy, should be energy divided by time. So if that is the case, then the heat transferred, within some time t is given as the power is equal to heat divided by time, and which is the same as, K times A times the delta T divided by the length. So this is the power. This is how the power is expressed. So this is how the power can be transacted. This is how the power can be transacted. This is how the power can be expressed. And it is being expressed as the rate of heat transfer, which is being given as the power. So keep this in mind. So different actually objects has got different actually conductivity. So here's the question for you: how the area, length, conductivity affect heat transfer via conduction? So I want to see the responses in the comment section below. Now, how about on the radiation context? So radiation is one of the mechanisms of the heat transfer that does not use the medium for the heat transfer. So in this case, let's say we have the object. Let me have this. Let's say we have, this is the object. Let's say this is the object with a surface area, and I'll call it as A. And let's say it is of a temperature given as T. Now this is the system's temperature. And let's say there is someone here. Let's say there is someone here, like this. And there is no physical contact between the two. That is the system and the person here. But now, how should we have to express the amount of heat that is to be transferred from this to this object, to this person, via radiation? Now, the heat flow will be expressed as the amount of heat is equal to the emissivity constant, which is the ability of this object to emit heat, times what we call it as, is said to be the Boltzmann constant, and that times the surface area of the system, and that times temperature to the power 4. Now this is times time. And if we express the heat transfer with respect to time, we'll have time of actually the heat over time, E times Boltzmann's constant times area times temperature to the power 4, which is the same as the power. So keep that in mind. So a temperature has to be given in kelvins. Now, this is the formula for the rate of heat transfer, this which is being expressed in terms of the power. Now, what if we consider that this is a region? Let's say this is the region with some temperature given as Ts. Now, in this case, this is the temperature of the surrounding, and this is the temperature of the system. So if that is the case, then what is the net what is the net rate of the change? Actually, what is the net rate of the heat transfer? Now, the net rate of the heat transfer, which is being expressed as the power, is being given as E times the Boltzmann constant times the area of this actual system, times the temperature of the system minus the temperature of the surrounding. By the way, the temperature has to be raised to the power 4. So this is how the actual formula for the net rate of the heat transfer can be expressed. So this is the temperature of the system, and which is the one emitting actual heat, and the temperature of the surrounding, the region which is receiving the heat. And basically it is the region with low temperature. So keep that in mind. So let's appreciate how we can have different questions associated with this. Now let's say this is the question. A glass window 0.33 should be a centimeter thick, measures 81 centimeter by 39 centimeter. So as you can see here, we have the length of the glass in terms of the thickness. That is the thickness. We have it as 0.33 centimeter. Of course, it has to be in meters. And it is measured 81 centimeter by 39 centimeter. And that will give us the area. That is 81 times 39. So area has to be given in meter square. Now we have to calculate the heat flow through this window per minute. So we need to have the heat flow per minute, which is per actually given time, which is the same as the heat flow per actually 1 minute. We should have that. So all we need to have is the value of the heat. So we should have to understand that the heat is given as, that is for conduction, is given as the Ka, times the temperature change divided by the length, which is the thickness, times time. So since we are to express this one, it means this time has been divided in both sides. So if that is the case, then we're looking for the heat per time, which is equal to Ka times the temperature change, divided by the length, which is the thickness. So by the way, change in temperature is given as 13 degrees Celsius. And the area is given as the area, which is given as that. Then we'll be able to express that one. That will be the heat transferred through the window per a minute. That is. Now let's consider this question as well. Assuming your skin temperature is 37.2 degrees Celsius, that is the temperature of the system. That is 37.2 degrees Celsius. And the temperature of the surrounding, that is the TS, is at 20 degrees Celsius. Now determine the length of the time required for you to radiate away the energy. Now we are looking for the time. We have the heat flow, that is 278 joules. We have been given the emissivity constant, which is 0.915, and we also have what we call it as the area, which is 1.78 meter square. That should be meter square, by the way. Should be the meter square. Now what's the formula? The formula is about the heat flow. It's about the heat flow or the heat transfer using the radiation. That is emissivity times the area times the Boltzmann constant, which is always been given, and times that of times, that is T to the power 4, that is the temperature of the system, and minus the temperature of the surrounding to the power 4, and times time, that is times time. Of course, we can also have it in this case, it also be the same as well. We can also have it in the same way, where we can have, okay, let's have it as a times time here. So at the end of the day, we have this, we have all these, and all this will be able to solve for time, or else we can use the formula for the actually net heat, actually net power, that is what we call it as the emissivity constant, area Boltzmann constant, to the power 4 minus Ts to the power 4. Of course, upon having the P net, you should have to understand that the P net is the same as the heat flow divided by the time. Since we have the heat, we can be able to have the time upon having the P net here. So keep that in mind. And let's also appreciate this question and see how we can make it up. Okay, the question says that find the heat that flows in actually 1.0 second. So we are looking for the heat flow. We have the time, that is 1.0 second, through the lead brick, which is 25 centimeter long. That is the length, 25 centimeter. Of course, it has to be in meters. If the temperature difference, that is the temperature difference, that is the delta T, it's 8.5 degrees Celsius. We have been given the cross-section area of the brick, which is 14 centimeter square. So the area has to be given in meter square. So you just have to convert that as well. So we are looking for the heat flow. This is about the conduction. So heat flow is given as, that should be Ka, change in temperature divided by, that is the length times time. So we have all these, we can be able to have the heat flow. So this is how we can have to understand about the concept behind the problem's approach on the heat transfer process. Thank you.